So today, let's talk about rate of change. All right, rate of change. You're right in saying that it is gradient, right? Rise over run. But in reality, what is gradient? What is rise over run? So let us say we have a graph. And the simplest way to understand that is, let's say, distance and time. Time here, distance here. And let's say these are hours or minutes or whatever you want to take. 1, 2, 3, 4, 5. And to ease the explanation, I will just talk about a linear graph. And let's say this is meters. There's 100, 200, 300, 400, 500. Now, rate of change, the full form should be rate of change of y value. Here that y value is the distance with respect to change in x value, which is time. The key point is the change. So if I say, okay, at t equals to 2, what was the distance? I mean, this is not a perfect graph, but let's say it's 100. So at t equals to 2, d is 100. This is just the measurement of distance at time t equals to 2. This is not the change. Change is what? If I say you have $10 and you spent some money and now you've got $4 in the pocket, what is the change? $6. So what did you do? Or basically, I say 4 minus 10. So basically minus 6. You've gone down by minus 6. So change always need two quantities. Change need two numbers across which you will measure the difference. And you said this is the change. If I would have said, okay, $10, and I say, tell me what is the change? You'll say nothing, right? 10 is 10. But the moment I say, okay, 10 has become 4, you say, okay, now I can do it. 4 minus 10. For change, you need two quantities. And rate of change of y. So I need two values of y in order to find the change in y. So let's say the second value is, let's say this is 300. Let's say the second value is this 300 and 100. So let's say my distance has changed from 100 to 500, 300. How has time changed? Time changed from 2 to 5. Rate of change of y. Let me find the change in y, which is 500 minus 100. With respect to means over ratio. Change in x. Change in x is 5 minus 2. So now whatever this computes to, so this is what? 3. That is the rate of change of y, or I call it as delta y, rate of change of y, or y2 minus y1 over x2 minus x1, or I can call it as delta x in the world of differential calculus. So this is rate of change of y with respect to x. In this case, the rate of change of y is nothing but change in the distance. And rate of change of x is nothing but change in the time. And I know from my knowledge of speed, distance, and time, speed is distance over time, change of distance over time, right? So this is also, for a distance time graph, this is also called speed. So in a nutshell, what we've learned is your rate of change. Now it is short form, rate of change. I will not say rate of change of y with respect to x. Rate of change. Y with respect to x is understood. Is nothing but gradient. And what was gradient? Rise over run. And what was rise over run? Y2 minus y1 over x2 minus x1. And we just saw here that this is what rate of change was. So this is the rate of change. Is nothing but gradient. Now this is when you have two quantities, x and y, fairly distant apart from each other. In this graph here, they were like quite far from each other, you see, the x and the y values. So this is general rate of change, or I also call it as average rate of change. This is also an average rate of change. The average rate of change is more applicable for nonlinear graphs. See, in your straight line graphs, you can pick up any 2 points, you will always get the same gradient because it is linear. Y equals to mx plus c. M is always constant. Whatever values of x and y you take, correct? You always get the same values. But when you take a non-linear graph, let's say you've got something like this. Now, if you say, okay, and same story, this is time and this is distance. And I ask you, okay, find me the rate of change between these 2 points. Let's say this is point A and point B. It's not linear. So in between A and B, if you start taking any 2 points, your slope will be changing. So that is why the slope, since the slope is not constant across this curve, the word rate of change actually becomes average rate of change now. So average rate of change will just average out the gradient, all the gradient values, the infinite gradient values between the points A and B. But I don't care about what's happening between A and B. I'm just concerned about the average rate of change. So I will just pick up the x and y here, and I pick up the x and y here, and the way I find out my normal gradient, I'll just go the same direction. So average rate of change is also y2 minus y1 over x2 minus x1. So a classic example here is, let's say you're going from your home to a point, to a destination, to a school, and your dad's driving the car, and let's say he started slow, and then he picked up, and then eventually he got to the point. That's the point of your school. And this was time t equals to 0, and this was the time, let us say it was 50 minutes. And let's say this distance was, let's say this is 50 minutes, and let's say the distance was 2 kilometers or 2000 meters. And I ask you, okay, tell me, what is your dad's speed? Now, your dad's speed was varying, right? So in that case, now since your dad's speed was varying, that means it's his slope of distance with respect to time was changing. He was driving slow, he was driving fast. So I am not interested in what his speed was at every second. I'm just asking, okay, tell me What was his average rate of change? What was his average speed he drove to? So just set, you've got time as 50 minutes, 0 minus 50, and the distance was what? 0 minus 2000 meters. So you can say 2000 over 50. So it's 200 over 5 is 40. So you'll say his average speed across the journey was 40 meters per minute. That's it. That is where the average speed comes into the picture. The average rate of change comes into the picture. Right? So that's the basic difference between rate of change and average rate of change. Rate of change is more for linear graphs. Average rate of change is more for non-linear graphs. Right? Where your speed or your y and x are changing every second, or whatever is your unit measurement of x that you're trying to measure against. Now, what is instantaneous rate of change? The last bit. Instantaneous rate of change is the change at one given point in its literal terms. So if you've got a curve like this, and I say, okay, give me what was his instantaneous rate of change here. Time, distance again. And let's say this was 10. And let's say this was what? 100 meters. This was like 10 seconds. Now you can argue that you just told me that you cannot measure the rate of change at one point. You need 2 points. Instantaneous rate of change talks about actually 2 points, but they are very, 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 very close to each other. So I still will take 2 points. So let's say I take 2 points here. And this is just because we are doing with naked eye. I mean, I can't get more closer than this. So let's say the second point was 10.000000000001 second. That's the point. So could you imagine how close these points are? Right? They will be super close. With naked eye, you could say they're just 1 point. Similarly here. So these 2 points will be super, super duper close to each other. They're as close that you can say that this point here is nothing but 1. One and the same. Why? Because if this is, let's say, t and this is d, and if I say change in t is delta t, which is t2 minus t1, let's say this was t2 and this was t1. So I'm saying that t2 minus t1 is nothing but it is almost 0. I cannot say equal to 0. The moment I say equal to 0, the fundamental fails because it becomes 1 point. I'm saying they're so close that they're approaching 0. They're as close to each other as from a naked eye, it could be just the same point. And hence measuring the rate of change at 1 point, which is t equals to 10 seconds, is as good as measuring the rate of change between the 2 points, which are very close to each other. So that is instantaneous rate of change. Again, the same story, delta D. Again, if it is distance over delta T, but there is a condition here. It says that delta T should tend to 0. The instantaneous rate of change does not hold any meaning if you don't write this. It actually tells us that the 2 points are so close that literally the change between them is nothing. It's negligible, almost 0, but not 0. And this is nothing but, we also call it by a very popular name as differential. So I will stop here and we'll go to the next topic now.